research engineer. You're recording. I'm working as a research engineer for Fraunhofer, Chile. Before I was working 2 years for Fraunhofer in Freiburg for the group of Agrivoltaics. There I was doing pre-feasibility studies, a lot of economic analysis, as well project acquisition, and then changed to Chile. Now I'm working since 3 years here in the team, not only in the topics of agrivoltaics, but as well different topics of integrated photovoltaics. So that includes floating photovoltaics, building integrated photovoltaics, urban integrated photovoltaics. It's a bit all of those topics here. In general, Fraunhofer in Freiburg is a really big institution with more than 1,300 persons. Here in Chile, we're smaller, so you have to be a more generalist at work, which makes it really interesting. You can dive into different topics and really learn a lot and move a lot as well here, because there's huge potential for some of those technologies. That's why it's really interesting. I've seen that a couple of people are studying the master's program from Latin America as well, and that is directed to people in Europe or all over the world. If you're interested in do an internship or you my email address at the end of the presentation, so you can contact me if you're interested in our work. Now we'll start with the presentation, Agrivoltaics, an insight into research in Chile, opportunities and challenges for adaptation to climate change. That's the title of today's presentation. And we'll go through 4 main topics. First, I'll give you a brief introduction of the work of Fraunhofer, Chile. Then I'll introduce the concept of agrivoltaics, concept of dual land use between agriculture and photovoltaics. Then on point 3, we'll talk about agrivoltaics as a solution to address central challenges in Chile. There I'll present some experiences of our research in the last couple of years. And then in point 4, we'll close the presentation with potential and challenges. This will be more a point of view from the legislation side to show you what barriers exist in the local market here and why agrivoltaics not yet is a commercial solution and can really unfold its potential for the energy and for the agricultural market. But starting with Fraunhofer. Fraunhofer is an institution that does applied science. We work in between university and the industry. So here in Chile, or in general, we got a funding scheme of 33, 33, 33. We got 33% public funds, 33% we have to apply to public research funds, and 33% comes from the industry. So the idea is really to generate results and apply those results in the industry, right? It's not basic science, it's more a applied approach, which is really industry close. Here in Chile, we have an office in Santiago de Chile, where we are about 30 people working in different topics. Fraunhofer mainly works from Germany and has its offices, its institutes there, but there's a couple of international offices or representations. The Fraunhofer, together with a center in Portugal, here in Chile, one more I don't remember. Those are the international centers where we really do research, really do work. The other locations are more people that do business development, that get into touch with local research and industry to at the end do projects in those countries. But in Chile, we're an independent institute that is working on a daily basis of projects. We organize ourselves in 3 subgroups: and photovoltaic systems, solar thermal systems, and new technologies. New technologies includes hydrogen, topic of batteries and electromobility. I'm working in the team of photovoltaics, but we have on site a really strong solar thermal team because we have really high irradiation level here in the Atacama Desert, the highest irradiation on Earth measured. So there's high potential for solar thermal technologies, for CSP, but as well for the integration of solar heat in industrial processes. That's a team on the side. They will focus on the photovoltaic part, but just if you're interested in one of those other topics as well, happy if you contact me. In the photovoltaics team, I'm leading the integrated photovoltaics topic that includes floating PV, agrivoltaics, topic of integration in urban contexts and buildings, and urban farm PV. There was a vertical agriculture project that is correlated to agrivoltaics as well. But that's the sub research line I'm working in. And to give you a short insight how we do work with the industry, we're basically in all phases of project development to support industrial partners. We do a lot of potential studies, conceptual studies to derive conceptual designs. And here in the project development, viability phase, we're quite active. And this is one of the examples. Most probably a couple of you guys like programming. We do a lot of programming, a lot of simulation in our institute. This is one of the examples, in-house software that we developed to simulate shade under the agrivoltaic system, which is one of the key steps in the design process. We derive conceptual designs and then verify those designs by shading simulations. Each crop under the panels or beneath the panels is facing some shade, right? And there's different shade levels that are good for plants, or there's a level where it doesn't, where it increases or decreases agricultural production or the quality of agricultural production. So it's really important step in the design phase to simulate the shade, which is one of the main developments we have in-house. And then in the phase of operation, you guys will see that we do quite a lot of monitoring and validation. And there we derive our studies from, and at the end of the day, quantificate the impact of the technology that it has in the agricultural part, but as well in PV performance. And finally, to close our activities, we work today, especially a lot in dissemination and policy. So they're doing technical assistance for the ministries. Because for the technology now in the Chilean government, there's quite a lot of interest coming up, which we're really happy about. And there we do consultancy. At the end of the day, provide scientific results to politics, so they take in the best possible decision. Say it like that. And from that, I'll start to introduce the agrivoltaics as the concept of dual land use. The first time the idea of combining photovoltaic panels and agricultural production on the same piece of land was published in 1982 by Adolf Götzberger, which is the founder of Fraunhofer-Institut for Solar Energy Technologies in Freiburg. That was the first time somebody communicated that idea. After 1982, there wasn't happening a lot because solar energy has another focus to bring down cost, really get on a commercial scale on an international level. There was less focus into the double use because it was not yet a topic neither, that maybe space is limited in Europe, or that synergetic need was not yet really present. So it was publicated. There was some simultaneous development in Japan, where they started in 2004, quite early, with the execution, commercialization of the technology. But there was not too much going on a global scale. In 2016, Fraunhofer in Germany started to work in the topic from new on. And why? Because they were seeing a problem coming up of limited land in Germany, not only in Germany, but in Europe, because the energy transition was in full process, which already was showing its effects, that there's limited space available. So they took this idea of the 80s of Adolf Götzberger and implemented the project. You can see here in Hegelbach in the south of Germany. At the end of the day, verificate double use of land within the German context, because that was the first pilot that was built in Germany. And from there on, the things developed quite dynamic. The project drew a lot of attention on the technology, big system with a new approach. So there was a lot of, in the news, in general, a lot of interest on commercial, but as well from a scientific point of view. And that really accelerated in Germany, but in Europe as well. And now I want to show you a couple of pictures, a couple of insights, because the technology is quite diverse. Right? We always communicate that the PV system is adapting to the agricultural context. And through this, we see systems that look really different. Right? So comparing the last system, there was an overhead system, 6 meters installed. So big machinery could work under the panels. We see here a vertical system where agriculture is done in between the PV row panels. So really different approach. Here not for horticulture or for animal crops, but to grow pasture or to have animals. Right? From PV side, it's an interesting system because you have peak electricity generation in the mornings, in the evenings, and we know the usually generation has a peak on midday, which as well creates challenges for the electricity grid. So it's an interesting function or dynamic of that system type. Going to France, this is a system in viticulture, combination with wine. Here we have a tracked system following sun from east to west throughout the day. But the tracking is not only performed to maximize electricity yield, but as well to create ideal conditions for the crops underneath the systems. Because throughout the day, the plant has different needs of irradiation. And the morning is really important that at the plant, a lot of irradiation arrives. That has a lot of light to activate photosynthesis. But then, for example, in southern France, at one point on midday, there was enough sun, so photosynthesis can't take more irradiation, really get the process up. And there, those panels can close down and shade the plants, which is really innovative approach, which is interesting to really maximize the electricity generation with the production of agricultural goods through a tracking system. Example from France. Here we see a system from the Netherlands with semi-transparent panels combined with raspberries. Here the main synergy and main motivation for installing the system is the protection of rain and wind. Right? With really that character of climate protection here, usually there's shading nets or protection nets above the raspberries. In this case, replaced by semi-transparent photovoltaic modules. And I was reading some results of that system recently. They have really good yield results under the system. Obviously, the semi-transparent PV panels, they're a challenge in cost, right? Because the special technology not produced on a scale as a monofacial, bifacial standard PV panel. But there was a certain or particular incentive of the Netherlands government in that moment, so that system could be installed economically. Here's a system from Germany, from Fraunhofer-Institut, and apple production in the south. And here as well, it's the main idea is to replace rain and hail nets within apple cultivation, as well with semi-transparent PV modules. It's a research system, like around 200 kilowatt peaks. And the interesting thing is that they implemented different system designs within one system. And there we see on the left, right, there's a different pattern within the semi-transparent module to at the end investigate the impact on crop development, but as well on PV performance. And there's some tracking within the system and some fixed approaches to at the end see which kind of apple tree, which technology works the best, and later scale the technology to commercial level, which is one of the main objectives of that project. Seeing all those pictures, we assume that agrivoltaics is as diverse as agriculture itself. And the really important part, and we always communicate that, it has to aim to create benefits for farmers. Now, it's really important that it's not developed on agricultural land to at the end steal those areas of agricultural protection. The main idea is to have adaptation, mitigation potential, or to create adaptation to climate change within agriculture to the installation of those systems, and really try to push that here in Chile and I think on an international scale. So it's really creating benefits for farmers. To give you an idea of the current development, today we are at around 14 gigawatt peak. on a global scale were installed worldwide. If we see Germany, for example, conventional PV in a couple of months, they installed 1 gigawatt per per month. So it's not a lot that is installed today. And the biggest part of that installed capacity we find in China as well, where really big systems were installed in the last couple of 10, 15 years. So there's some development in Europe, but of those 14 gigawatts, there's not too much placed in Europe and in Southern America neither. That is the introductive part, and now I want to look into some research results. Agrivoltaics, a solution to address central challenges in Chile. Then we'll look at a couple of studies. A study is related to PV performance, to soiling. A study is related to the microclimatic impact of the PV panels in agriculture, and a study based on geospatial data to identify potentials within the country. And there we start with challenges, two major challenges we face in Chile. Here is a statement of the energy minister of 2022. Chile needs to add another 30 gigawatts of renewable energy in a decade. So this is quite a lot. We have installed 9 gigawatts today. There's a lot of space in Chile, but the extension of the electricity grid is one of the major limitations to install more capacity. There's a lot of missing the English word, but the electricity lines are full. Basically, you can't connect systems anymore in certain locations. So the extension of renewable energy is a challenge. From agriculture, from climate side, Chile is one of the countries most vulnerable to climate change. We have a drought since 2010. Last year was a bit of an exemption, but there's a lot of water missing in the central part of Chile, which already is impacting agriculture really strong. To give you a fact, there's more than 300,000 people in Chile living off water of trucks because there's no more water accessible in those areas where they live. And this is really taking up. So water is the key resource that is critical in Chile. We started working in the topic of agrivoltaics in 2017 here in Chile and installed 3 pilots within the metropolitan region of Santiago, where I do live. Here on the map, we see Santiago on the right, a bit in the outskirts of Santiago. We installed those 3 pilots. 3 equal pilots with a capacity of 13 kilowatts, so quite small pilots, as you see, with a vertical clearance, so a height from the PV panel to the ground of almost 4 meters and a surface of 230 square meters. Installing 3 pilots to, from one perspective, investigate different PV performance depending on the location. As well, they have different azimuths, orientations to the trajectory of the sun, but as well to create a social impact, because the project had as a main objectives to create a social impact. So installing those systems within 3 agricultural productions together with 3 farmers was creating a bigger impact than just installing one big system. And today the farmers, they're owning those systems, they're using the energy that it is generating, and they're working under the panels. And there we collected some practical experience. So first, it's always great to go out and talk to the people. It's great to leave the office once in a while. And it's interesting, the sun is really close. It's really strong in Chile. So farmers really like to work in the shade at the end of the day. We see on the right a good example. It's good to have a rest or to really work in the shade. And we see on the left that the farmers can work with their usual machinery without barriers, without limitations, which was an important point as well. That was the practical experience a bit. And from there, we want to stick to the pilot, to a microclimate study we did last year, asking us what impact does the installation of photovoltaic panels have on the agricultural context in terms of microclimate and agricultural yield. And there, as I showed you in in production. We work in the operation of those plants, installing sensors and measuring parameters in the field. What we measure within 2 stations underneath the panels, we got one reference station outside of the system, and you see in the background picture on the left, we got another station under the PV panels, and then we measure irradiation with a pyranometer to compare. What we measure is that solar irradiation decreases by 30 to 40% within the course of the year. On the right, we see the curve with solar irradiation on the vertical axis and the time of the day on the horizontal axis. There we see the green spot or the green curve, which is basically the data we measured underneath the panels. And there we have quite a low on midday, which is a good sign, which is a good result, because as I explained before, many of the crops need the shade on midday to be protected of sunburn, to receive too much irradiation that at the end gets up water consumption. So quite good result as well. We did the design of the system to 35% of shade, so that verified our simulations as well in that sense. Based on the data we measure in the field, we do compute evapotranspiration. Evapotranspiration is the amount of water that is lost by the ground, combined by the plants through the leaves. So how much water is lost through the impact of sun and to the impact of wind. And then we measure the microclimatic data and simulate with a methodology of the Food International Organization, the evapotranspiration rates. And what we compute based on the measured data in the field is that we can decrease irrigation demand by 31%. And that reflects in irrigation, that we can lower evapotranspiration demand by 31%, which reflects in a reduction of irrigation demand by 31%, which is a really important parameter. If we look in those locations within the central part of Chile that really have a lot of problems with water, it aggregates a lot of value to lower the irrigation demand by 31%. A really important parameter in the communication with policy as well. As well, we measure soil temperature. We measure a lower 2.8 degrees lower soil temperature. This is an important factor because for the productivity of photosynthesis, the leaf temperature is a really relevant parameter, which can be directly correlated to the ground temperature. And if we look at air temperature, we see less fluctuation in comparison to the open field. So we have a stabilized air temperature under the system, which gives the hint of additional synergy in fruticulture in central Chile. It's a challenge when freeze is coming up, especially in springtime when the trees are flowering. So there you want to avoid the freezing, because through that you'll lose the yields. So that stabilization of temperatures, higher temperatures at night, lower temperatures at day, can have a benefit to that challenge. And at the end, our computation of evapotranspiration, we confirmed through measurements of soil moisture within the fields. We measure almost 30% higher moisture underneath the panels, which connects to the lower evapotranspiration rate we measure or we computed. And then finally, which is not my particular field, but which is a valid question, our plants growing underneath the panels, that we did some analysis, more rough analysis here for salad. In that case, where we found same yields within summer. It was the same for broccoli, but depends a bit on the time of the year. But there a lot has to be done in research to create local results that would inform farmers and as well create confidence within farming, right? So that the plants keep on growing the same way or even a better way, or have small yield losses under the panels. From there, I want to present you a couple of results of a soiling study we did, asking us what impact does the installation of photovoltaic panels in the agricultural context have on photovoltaic generation. Well, we have in that kind of technology, we have a new context of installation, right? We install the panels combined with agricultural production, which we haven't done before. So through that agricultural production, we would expect there's a lot of dust coming up, especially in the arid, semi-arid climate of Chile. There we went to the field a couple of times to measure the IV curve of dirty and clean PV panels, measuring typical data with reference cell, with a temperature sensor to derive cell temperature. There you see my colleague in the field, and there you see how we're cleaning the panels, right? To get the performance ratio for the clean panels and for the dirty panels. The one you know most probably from your studies if you're doing solar engineering. And applying this study, we went a couple of times to the field to measure the performance ratio. We observed a steady decrease in performance ratio in the dry periods and a strong influence of the cleaning episodes, which is something we expected. We see in the curve how we start from 60% performance ratio going down to 40 from November to January. Then we have a rainfall that lifts up performance to 80%. Then we have a cleaning event in February. Interesting to look at is the agricultural activity, right? And it makes sense, the connection of lifting performance ratio with cleaning or with rainfall. But here looking at the agricultural activity on plowing and furrowing, which are agricultural activities at the end of the day, not really necessary to know the details. But we don't see a strong influence of this agricultural activity. What we analyzed is that we have on the side a public road, which is made out of dust at the end, which is made out of dust that has a strong influence on soiling rates. But agricultural activity specifically didn't have a measured or a visual impact here, right? Because the curves were going down within the same magnitude. A couple of numerical values we don't have to spend a lot of time on. At the end is the question, to what extent does that affect agrivoltaic systems in Chile? We measured high soiling rates of 0.35% per day, which sums up to 10% per month, which is quite high in comparison to conventional systems, which basically tells us that we need solutions for cleaning, right? And cleaning at the end is a challenge within the height, which can cause high operational cost. So that's important to look at robotical solutions or already in the design phase to think on operation and maintenance. And with those results from the agricultural point of view and from the PV performance point of view, I want to close with potential and challenges. Here we did a geospatial study asking us what is the potential to generate electricity and protect water resources for a particular crop in Chile. And here we did a study for blueberries because it's a quite high value crop. It's grown quite a lot. We see here on the low part of the slide that 5% of the fruit growing area in Chile is blueberry. There's quite high economics in exporting that fruit. There's high expectations on quality, which connects good to agrivoltaics and its protection synergy. And there's a lot of plastics used at the end to protect the berries, right? To protect the production. Production is going up recently until 2022. It's a good crop to look at. And there we analyzed data to look to first identify the areas through Chile. There we identify the major areas within the central part. You see Santiago in the middle of the country, and Chile is a crazy country in that sense. It's 4,300 kilometers of length and an average 200 kilometers of width, with really special form, having many different climatical zones throughout the country. The Atacama Desert in the north, Patagonia in the south with a lot of rain, and the arid to semi-arid climate in the central part. And you see that agriculture is focusing on centralizing in the central part. In the north, not a lot of agriculture is possible due to the lack of water. In the south, there's a lot of forests and really extreme weather as well. So we identify those areas here in the central part. That is doubling. And when we apply a certain system design on those areas, we identified 13 gigawatt peak of additional PV panel capacity we could install without losing productive area at the end, which is an interesting fact. We see that all regions south of Santiago have quite distributed potential of almost half of a gigawatt peak. And here the Maule region, which has a lot of fruticulture, has the biggest potential. What is interesting to looking at those results, the distribution of the PV capacity is installed today. That's 6.9 of current PV capacity. That was in 2021. But if we compare the distribution, we see that the majority of PV is installed in the north, in the Atacama Desert. But we have the main demands of electricity in the central part, right? Around the region of Santiago, O'Higgins, Valparaiso, which you would see on the right. And we see those potential areas and the potential generation is all located close to the demand, which gives us a good hint of one of the major synergies of technology for distribution generation to provide electricity close to the demand, which is something really necessary in Chile due to the limitations of the electricity grid from north to south, from generation to demand, which I mentioned briefly before. What we looked at as well, we did compute evapotranspiration to look at how much water how much less water we need in agriculture to irrigate. And there the results are really interesting. There's a total potential to produce almost 18 millions of cubic meters of water per year due to a irrigation demand reduction of 15% under the applied agrivoltaics PV design. The number is quite hard to grasp, I think, but what is important, if we correlate the areas we identified, the blueberry fields at the end of the day, to the areas that were affected by water emergencies that are related to the strong drought we're facing since 2010, we see that the majority of the blueberry fields is located in those really highly affected areas. So through implementing the technology, one could really create a relevant synergy to bring down irrigation demands. And that was a short insight on a potential study. What we see based on these potentials, we've shown on the investigation that was done that first commercial systems are developing. There's one commercial system so far we visited the other week by the company O Energy, which is called Isla Solar. They have cherry trees in between conventional photovoltaics almost. It's a different approach. It's the first commercial system here in Chile with 9 megawatt peaks combined with cherries that you see us in the field on the right. Good project with 2 agronomists as well to do the agricultural analysis. What they adapted on the PV design is only that they elevated the trackers, it's a track system, by 1 meter, right, to avoid shading. And then I'm closing with the last slide, legislative analysis. However, why is there no broad commercial development of agrivoltaics in Chile? What can we learn from international experiences? To show there's potential benefit for agriculture to the water topic. There's a lot of generation potential for Chile, especially for the push distributed generation. So why is there no development? There we identified together with the ministries 3 central challenges. First, research. There's not a lot of results on a local scale. I mean, we do research. There's a couple of universities working on the topic. Really, results from the local context are missing. From international developments, experiences, we can always learn. I mean, there's really advanced projects in Germany, in India today, in Europe, financed by Horizon. So there's good projects we can orientate on. Second is profitability. Due to the adaptation of the design of the PV plant to the agricultural context, we face higher costs, which is a challenge, especially for Chile, as really neoliberal approach to manage its energy market. So there's not a lot of subventions or political help, right? That is a second topic. And third is legislation. There's no normation of the technology. There's no differentiation between conventional photovoltaics and agrivoltaics, which causes insecurity at the end in the sector to implement that kind of systems. So coming back to the title of the presentation, Agrivoltaics, an insight into research in Chile, opportunities and challenges for adaptation to climate change. We did identify potentials and challenges. First, the potential for climate change mitigation, right? Through the generation within distributed generation in Chile. So there's a lot of potential because there's a lot of agricultural surfaces. Second, adaptation to climate change. There, the topic of water is a high potential for Chile because the country is facing huge drought and there's no projections that will get better. And third, we identify significant gaps for commercialization in investigation, profitability, and legislation. We have to work on from industry side, but as well from policy side. And with this conclusion, I'm closing up my presentation. It was hard to present a bit in English, speaking so much Spanish today, but I hope.
Not at all. It was great. Thank you very much for the presentation. It was very interesting. We already have here a few questions for you, and to everyone, you're welcome to either unmute yourself and ask the questions or write them in the chat box. Here we have a question from Ronald. He refers to the slide 30 to 34, and he says, as cleaning was done after a rainy season and later plowing was carried, so the soil should be wet, isn't it an error to measure impact of plowing on soiling because soil was wet?
Sure. I think, so in general, it's raining here one day, but then the sun is coming up, and in the course of 1 day, 2 days, soil is really drying out. In general, if there's agricultural production, everything is irrigated, right? But in that moment of plowing, there was no cultures, so there was no irrigation. But I don't remember how close the measurement was, right, after plowing. But usually the soil is drying out really fast. So if there were a couple of days in between, it should make sense to go there and measure.
Yeah, thank you as well, Ronald, for your question. We also here have a question from Asha. Given Chile's water scarcity challenges, how is the nation planning to address them to effectively pursue its green hydrogen strategy objectives?
Yeah, the green hydrogen is the big topic all over Chile, especially in the northern part, in the Atacama Desert, right, in Patagonia as well, based on wind power. So the water, where is it coming from for the hydrogen? That's a really good question. All the projects I see are basically the current developments. It's more hubs and more on a pre-feasibility level than on a implementing system level. There I see that's all desalination. So all getting out the water of the sea and using that water to derive hydrogen. So all seawater.
We also have a question here from Francisco on how about like referring to the previous answer that you gave concerning plowing. He said, how about vertical bifacial PV? Would that reduce the dust problem?
So yeah, so what we see in vertical PV that we basically don't have to do any cleaning. It depends a bit on the climatic context as well, right? In Chile, as we have really dry context, the dirt, which is basically dust, it's not sticking a lot to the panels. So really low soiling rates to no soiling. It's a bit different in Germany if you have really wet ground and the farmer's working next to the PV panel and there's a lot of dirt coming to the panel. But here in Chile, at the end, it's an approach to avoid those higher soiling rates and to have less OPEX cost at the end. So it's something relevant. It's a benefit of vertical PV, let's say.
Right, thank you. Here we also have a question on if there are available studies / data on which crops are suitable for this technology and which are not.
So there's I've read a couple of reviews recently. There's from 2003. There were a couple of reviews written that addressed that challenge quite good. I mean, they resume information from international studies, try to systemize what the crop response within agrivoltaic systems, but unfortunately, there's no general answer. Right? It really depends on the climatical context and as well on each specific case. I'm not an agronomist, but in general, there's a triangle of how a crop develops. It's water, soil, and irradiation, or at the end, microclimatical or climatical parameters. Irradiation plays a crucial role. If you install a system on degraded soil, for example, to reactivate that land, then you can basically implement a shading rate of 50%, 40%, depending on the crops, because the plant growth is limited based on the soil, right? You have really good condition of water and of soil, then crops are quite sensible on the irradiation. So it's really depending on the context and on the climate as well, right? That would be my answer. My answer would be to read the review papers because there's some good information put together.
All right, and we have also here a question on if there is any incentive in Chile for regular people to implement this kind of solutions for energy generation and improving water savings, and also any steps that Chile has taken to address energy transmission issues from north to central regions.
So answering the second question first, to address those limited capacities in transmission, there will be a direct current line installed until 2032, I think, which is quite a lot of time because you would have to keep on going with the energy transition, right? But that's a big measure. It's 2,000 kilometers, 1,500 kilometer power line from north to the south to address that bottleneck. The first. And second, there's new incentives of the government for mid to big scale battery systems, right? To inject or to get the energy in the batteries in the Atacama Desert through the day and inject at night. There's some incentives created by the government that too. And now it's moving from political side to get the first call specifically for agrivoltaic systems, like innovation call, but connected to the implementation of irrigation systems. So it's more coming from the Ministry of Agricultural side, where they finance the irrigation systems, and that those combined with agrivoltaics. But we're in the design phase together with the ministry for this year. Most probably next year there'll be a tender where small scale systems can be installed together with the installation of irrigation systems, which is great development.
Yep, definitely. And here we have also a question from Rami, maybe the last question, unless some people have other ones, on what are the main durability challenges to agrivoltaic systems in Chile?
Durability?
Although,
yeah.
I think there's a follow-up question. Maybe we can answer that first, and then there's a follow-up question from another person. But yeah, the main durability challenges to agrivoltaic systems in Chile.
I think it's robbery. Yeah, there's quite a lot of robbery in PV systems, which is a challenge. Which is a challenge for operating cost, and I mean it's super hard to control on the countryside, right? Yeah. That's somehow related to durability. But beside of that, it's really dry context, so we don't have a lot of corrosion. What we do have in the northern part, we have really high salty soils. So their corrosion of the subconstruction is a big topic in conventional PV, but for agrivoltaics, not that much because those soils are not really good to do agriculture.
And another question here on if implementing this technology requires an effort to convince farmers to do so, or they actually are the ones who express the initial interest.
That's a good question. That's a good question.
Mhm.
So I would separate agriculture. In Chile, we have a strong fruticulture sector that is exporting food, right? China to Europe, to Northern America, to the big market. Those are international, multinational companies that are quite open to innovation. So if they see a payback and they see a benefit for their cultivation, they're quite open. But obviously on small scale to mid scale farmer side, it's quite hard because they work as they work since 100 years, and there's not a lot of adaptation potential on that side. But we would like to push the technology not on the not for the big companies that already have enough money, right? That have less economic problems, that are less vulnerable to climate change. It would be important to implement it on a small to mid scale. And there, really communication in between the sectors is really one of the main challenges. So that's why it's important to always work together with entities from agricultural side and have in the best way a agricultural engineer or agronomist that communicates the benefits and the technology to the farmer, because we as PV engineers or as mechanical engineers, it can be quite hard to think through those eyes to a person that is doing agriculture.
Yeah. Do we have any final questions from the attendees? Yeah, again, thank you very much, Frederik, for your time, for the interesting presentation. Thank you very much for being with us. And also big thanks for all the attendees as well.